I'm not going to go through the proof of the derivative of tan inverse. However, if you'd like to see the proof, it's in the textbook and you can work through it. Probably not much more for you to gain from going through that proof to the other ones, or the sine inverse one. So I'll just leave that up to you as to whether you have a look at that or not. So by definition, the derivative of tan inverse is 1 over 1 plus x squared. And again, what do you notice? Well, hopefully you notice that the derivative has nothing to do with a trig ratio. So what does that then mean? It means that when you are given an integration question, you need to recognise this fraction, that if you were integrating that fraction, it would take you to a tan inverse function. I suppose that's the easiest format. Tan inverse of x goes to 1 plus x squared inverse. The derivative of tan inverse x on a is a over a squared plus x squared. I don't know, neither of those are on the reference sheet. A form of the reverse of this is, but what is actually on the reference sheet is this one here. So, and if you think about the integral 1 over a squared plus x squared giving this 1 on a tan inverse x on a, if you are differentiating 1 on a tan inverse x on a, differentiating that's really nice, that's straightforward. You will see a lot of questions where, though, you don't have this 1 on a, but you might have x over a number. Well, we've dealt with that before. We know that if the constant isn't there, or in this case 1 over a number isn't there, then we need to introduce the a and compensate and set it up so that we could integrate. Hopefully that's not too confusing. Let's have a look at some examples. Just some things to point out. Remember that, or just take note of the way that this fraction is different to the sine or cos inverse. So with both sine and cos inverse, we had a square root in the denominator. With tan inverse, there's no square root. And there is the 1 plus, there's a plus before the x squared. Just those little features, I think, might, if you are aware of those, it'll help you to identify when you are differentiating and integrating, that you don't have the square root when you're differentiating, and you have a plus sign, and when you're integrating you're looking for, if there's no square root in the denominator, then you'll know that it's going to a tan inverse. And be on the lookout for the x squared, otherwise you might be thinking log. So yeah, just have to really focus on what your answers look like now, because your answers will be possible future integration questions. So you can see here with differentiate y equals tan inverse 2x, I've considered that, look, a little slightly complicated. You can always use dy dx is dy du times du dx, and so why not in this case? Let u be 2x, du dx is 2, and y becomes tan inverse of u. Tan inverse of u, very easy to differentiate. So dy du is the 1 over 1 plus u squared, and multiplying by du dx, which you can see there is 2. Sub u back in, for, or sub 2x for u, and you get 2 over 1 plus 4x squared. And then we see an application when we start talking gradient. Then we're using our understanding that the first derivative is an expression for the gradient. We know the value of x in this case is minus a half. You've got a fraction 2 over 1 plus 4 times, and I would show every step. So show the step where you're subbing in minus a half. Because what I'm finding for some of you is that we would call that mental arithmetic, because you're doing it just mentally, you're not writing down, is not that strong. So if your mental arithmetic is not that good, then write down every step. So we've got 2 over 1 plus 1, which is 2 on 2, which is 1. So the gradient of the tangent at x minus a half would be 1. And I'll stop the video there and you can get started on some of these easier questions in exercise 1.